now, I'll give you just a brief introduction of about the wind turbine, and then we'll jump into the implementation of horizontal wind turbine system of 5 kilowatts. We'll do the definition and then see the aerodynamic lift and aerodynamic drag wind turbines, type of wind turbines, mathematical modeling, and Matlab modeling of the simulation. Uh, the wind turbine has been for long. Initially, used to use for the windmill or for irrigation purposes as like a pump and suck the pump of water from the well and then irrigate it. Even after later on, it was started to use as an electricity system to harvest the energy from the wind and to convert that into an electrical energy. Uh, Normally, if you look at the size of wind turbines, you can find from commercially available wind turbine, the 100 kilowatts to several megawatts. We'll have two type of wind turbines, horizontal axis and vertical axis. Um, Different parts of the wind turbine. We have a rotor. It's full diameter. It's called swept area. We have rotor blades. Normally, we'll discuss about the horizontal axis wind turbine. Usually, there are three blades in the wind turbine, but you will find some of two blades as well. So after the blades, you'll have a gearbox, and then at the end you have a generator, and this part is called nacelle. And then you have a tower where this wind turbine is standing, horizontal axis wind turbine. About the mathematical modeling, you have kinetic energy flows through the air in a perpendicular direction, and it's half v square per mass flow rate. This is the flow rate for that. Using that, they have calculated power of the blades as Cp times power of wind, which is Cp is a power coefficient. We'll discuss later on. So Cp times half, rho is the air density, air is the area, swept area of the blades, and V is the wind speed, prevailing wind speed. Normally, the optimum speed is of the wind speed where you can get the maximum power is between 10 to 15 millimeters per second. Yes, of power factor and it's just CP, and theoretically you can get the 0.593, which means that 59.3% of the wind can be converted into the power, which can be translated into electrical power. And there are other coefficients. One of them is blade angles, which is called beta, which is called pitch angle. It's defined as the angle between the plane of rotation and blades cross section chord. And you have another important ratio, which is called tip speed ratio. It's called lambda, and it's directly proportional to rotational speed and the radius of the wind of the swept area, which is like a length of the blade, and it's inversely proportional to the wind speed. So omega m is the angular velocity, r is the rotor blade length, and the v is the prevailing wind speed. If you look at the characteristic curve, between the power and the tip speed ratio, power coefficient Cp and tip speed ratio, we'll find the maximum power coefficient can lie between 8 to 12, which is 8 or 9 tip speed ratio, which is lambda could be 8 something. You'll find the maximum power coefficient. We can find the rotor torque. The rotor torque is the power of the blade divided by the rotational speed, where it's Cp lambda rho A V cube over omega m, where A is the area, swept area is pi r square. So if we include that into area, so rotor torque, it's power blade over omega. So 3.1.9. It's equation for the calculating the torque of the wind turbine. The power coefficient Cp is a non-linear coefficient, and it depends on the pitch angle and the lambda. So this is in research papers you can find Cp is equal to C1 into C2 times 1 over omega minus C3 into beta minus C4 into beta x, and so on, and into e is from minus 6 over 1 over lambda, where lambda is defined as 1 over lambda is 1 over lambda plus 0.08 beta minus 0.035 of 1 plus Cp cube. That is the what's called a tip speed ratio of 1 over lambda 5. And coefficient C1 to C6 can be found in the numerous research paper as 0.5, 116, 0.405, and 21. And X is not used here because C4 is 0 here. You'll find the tip speed ratio is lambda is omega r times r over v. Omega is a rotational speed of the shaft in radians per second. Here is a typical example of omega at 0.09 and radius is 35 meters and beta is 0 degrees. At different wind speeds, you find this. The maximum Cp is given around 8, which is lambda around 8. So you find, and it's about 4 point something, 0.4 something. That's the maximum that you can extract. Ideally, it's 59.59 something, but usually maximum you can get so far is 0.4 something. Cp would be found maximum is 0.41 something so far. Here's some calculation where we want to find out the different parameters for a 5 kilowatt wind turbine. So we have the power, which is 5,000 feet. Use this power equation. So that will, so we power is 5,000 and then we said as wind, rho is air density, and it's normally air density of air is 1.2 to 5 standard. So if we plug into this values, and then we have optimal speed is 12 millimeter per second. So we need to find Cp and we need to find R. In order to find Cp is 1 over lambda and beta. Beta, we keep it as 0. So we can find 1 over lambda that will give us, and we plug in this value of when we find the lambda is omega r over v. So we can find Cp as 0.41034, and then we substitute that into this equation. We find our radius is 1.9141431 meters. Lambda, typical lambda is from the equation. If you plug in this into you find 11.34. and omega r could be find is 55, 50.775. So these parameters will be using for the MATLAB simulation. So I'll switch to the MATLAB now. Let me go side by side so we can. So we need to find out the power. So power is equal to Cp times rho times area times V cube. So we need 4 parameters to find out the power. So we need 4 inputs. So we get 4 max, 4 of the, we get a mux and we get 4 inputs from the mux, and then we calculate a function. So let's find the function from the Simmulink library. We go to user-defined function and we take the MATLAB function. Okay. All right, so let's define first the inputs. So first input could be according to the equation, we can say rho area and velocity. These are the constants that we can get it, and Cp we can calculate it. So we have we get an area. Area could be calculated uh, by the radius. So we need an area here. So let's say it's U1. This is U1. And area, so we get velocity, wind speed. You can call it U2. And then we have a constant rho. We can give a constant here. We give its value 1.225, and that will be U3. And then fourthly, we have our CP, that will be our U4. So first of all, we need to find the area. So we have an input, and input is the radius, so it will be so you can say this one is our radius. Okay, that will be meter. So we need a radius, area is pi r squared. So we can have a gain here. And we can have a function here also. So we can make it like, here's equal to u1 square, r square. And then it will be multiplied with a pi. So we can have pi here. So that's our area. So we got area here. Now we need second thing is v, wind speed. That will be v cubed. So we need another function. And we said it's v, 6 meter per second. Need v cube here. We can find v cube. No, just v. Disregard v function. We just directly give it. So we'll find. We'll do the v cube there in the function. No need for second function. So we have v here. That is u2. All right, then we have a row here. And the fourth one is CP. So for CP, we need look at the CP. Equation CP, we have 1 over lambda, beta. So we have two coefficients, and the rest of them are constants. So we need beta and lambda. So we'll have a function here for the CP. And we'll have a mux here. have two inputs in the mux. All right. So we'll have beta. So we can have another input, which is a beta. Okay, that will be here. All right. And then we have a 1 over lambda. 1 over lambda will have another function for that. And this 1 over lambda is as a lambda and beta, two inputs. Yeah. As another we need There we go. Okay, for lambda we need lambda and beta. Okay, so beta is here. Beta is and lambda. We need to find out lambda by omega r over b. We need another input as omega r.
Assalamu alaikum.
Alaikum salam. How are you?
Alhamdulillah, just joining because I have class.
Alaikum. Tip speed ratio is lambda. Now we need omega r, sorry. Just we have to find out rotational speed. Rotational speed is radians per second. We have it here. We need omega r and a radius also in lambda. Oh, okay, sorry. This was lambda. We need to have some space here. Okay, that is CP. Draw it here. Rotational speed is still. And the rotational speed is here. We need to find a lambda. This is lambda here. We need to calculate lambda. All right, so lambda is omega r into r over v. So we need two multipliers. In the product. And let's me do again. Let's see. We and divide by v. And this is lambda. It's beta. Right. We need a saturation block. So we are dividing. In case if divisor is so small, it will go infinity. So we need a saturation block here. And we use it here. We go higher one is infinity. Lower one is 1 exponent minus 6. We don't want 0. Okay, that's okay now. Control R. So I got there. All right. So that's that. So we got lambda. That's 1 over lambda, 1 over lambda CP. So CP needs beta and lambda. Okay, and that's rest of them are constants. So let's do 1 over lambda first. 1 over lambda is you have lambda plus beta, two of them. Which one is lambda? Which one is beta? This is beta. One is beta, two is lambda. Okay. One over pi u2 plus 0.08 times U1 that is this minus 0.035 divided by 1 plus beta is what? Beta is 1. U1 cube. That's it. So that's our 1 over lambda function. That's going to Cp. Then now let's calculate Cp. So Cp has constants. So we have C1. C1 is 0.5. 0.5 times C2. C2 is 116 times 1 over lambda. 1 over lambda here is 1 over lambda is 2, U2 times U2 minus C3. C3 here is 0.4 times beta. Beta is U1. Let's see. Beta is U1 here. We go 1. Then we have minus C4. C4 is 0, so this terms become 0. Then minus C5. C5 is 5. 5. Then we have exponent of minus C6. C6 is minus 21. It will be minus 21 times 1 over lambda. 1 over lambda is U2 variable. Let's see. Here is U2. That will be U of 2. That's it. Let's see, no errors. So now we got Cp, so we need to find power. What was it? It's only 4. Okay. That will be our power. Let's do this. So power equals equation is it's a Cp times half times rho times A times V cube. We have all multiplication. First one is area. Second one is, let's see, this is 3. This is U1, U2, U3, U4. Okay, so area is 1 and U2 is V. Okay. So that's easy. So we have 0.5 times U1 times U2 times U3 times 4. That's it. 1, 2, 3, 4, 5. 1, 2, 3. Good. So that is our, let's see, what is this? Delete that. So now, if you go back, we have the subsystem, which we have a radius, so that's about 5 kilo. Yeah. We need to give inputs, and so now we look at our calculation we did. We saw that for 5 kilowatt, we need these parameters. The pitch angle, which is beta, is 0. Radius will be 1.91431 meters. Lambda could be like this. Omega r, rotational speed, could be 50.775, and v, meter per second is 12 meter per second. So we need to get these constants here. All right, so this radius, we got 1.914. 1.91431. Okay. The other one, all right, 12. Well, velocity is 12. Beta we give 0. There's no pitch angle, we are giving simple. And rotational speed is at 50.775. Okay. And we have a display. Power. All right, hope everything is okay, no errors. Let's try. Oh, okay, we need to have a power GUI. run this model. All right, let's try Bismillah. Okay, it's not giving what we expected. It's giving 34.73. There might be some mistakes that I'm doing. So anyhow, this I did the other model. It gave me the correct answer. So this is how you can implement uh, the first part of wind turbine. I'll post. I'll share with you the original simulation, which actually gives 5,000 watts or 5 kilowatts. Um, this is as you see, wind turbine has different several parts. This is the first part, which is the rotors and blades, and that's called turbine. So we have calculated the power the turbine. The next stage is we have to increase the speed because turbine does not run as fast as we so we can generate the energy or generate the power electrical energy. So second part is a gearbox which increases the speed of the turbine, and the third part is a generator itself which generates electrical energy. So that's why I've divided this into three parts. The first part is for turbine. Second part we'll try to squeeze second and third in a one gearbox and the generator in one, and then we'll see the uh, power is generated, 5 kilowatt electrical energy is generated through this system. If you have any question, please, I'm open. Anybody? If not, then
Thank you very much, Brad.
yes, yes.
And friends, please try to fill your attendance and as well as the survey link, which is shared in the chat boxes.
There are 12 participants here, so okay, thank you. All right. If nothing, then I'll leave you go, let you go. Thanks for coming, and I'll announce the second part. Then we can continue from there. Thank you.
Thank you, brother.
You're welcome.